Good day everyone and welcome to this lecture. In the previous lectures actually we started studying regarding the treatment process, and there are basically 3 stages of any water or wastewater treatment, and those 3 stages are physical, then followed by physical, it may include chemical as well. So, it is physico-chemical, followed by biological treatment which is also called as secondary treatment, and then tertiary treatment which is generally also physico-chemical in nature. And there are various unit operations which are followed in all these treatment methods, and these unit operations may be placed in the treatment unit at different places. So, within a effluent treatment plant, these treatment units or unit operations may be differently placed depending upon the characteristics of the water, amount of water being generated, and also the what is the requirement or designated use of that water later on. So, depending upon these units are placed. So, among the primary treatment units there are a number of units which are there, and in the last lecture we studied regarding the flow equalization basin. So, flow equalization basin, what it does is that it equalizes the flow rate, and also it homogenizes the characteristic of the water. So, further treatment is easy, and also the secondary units and tertiary units which are there, they can always operate at maximum condition or optimized condition, and their efficiency is maximized. So, flow equalization basin is one of the first units, it may be there along with some other pre-units which may be like removal of grit etc., and after that flow equalization basin, and after flow equalization basin there is a high possibility of an aeration unit also. This aeration unit may also be mixed with the flow equalization basin itself. That means, the aeration may be performed within the flow equalization basin also. So, there is a high possibility. So, today we are going to start section on aeration. We will be studying aeration in great detail, and in one of the lectures like today we will be trying to understand the basic formulas by which the solubility of gases at any temperature in water may be calculated. So, this is very important, and it depends upon Henry's law or Henry's equation, and using the Henry's constant we can determine lot of all the solubility of gases in the water or wastewater. So, certainly some alteration is required for determining the values in actual wastewater, but we will be continuing this basic information further, and we will be trying to study the what are the aeration things, how the aeration can be found out, what is the rate of oxygen transfer or air transfer, and how it is dependent upon various mass transfer resistances and other things. So, this will be the second step within the aeration after the first basic step with respect to solubility. Thereafter, we will try to understand that what are the various aerators which are commonly used in the industries as well as at various treatment plants which are there, and thereafter we will try to solve some of the problems and understand that how we can do the preliminary design of a aeration unit with respect to finding out the volume of the unit etc., under certain conditions. So, this is the plan for whole plan for understanding the aeration and other things. Now, aeration is very common in day to day life also. We see aeration we see aeration while going to any hill station, like in Nainital if you go, you will be finding that if you are on the top of the hill looking at the Naini lake, there is some bubbles, big bubbles or big things happening inside the lake, and actually what is being done is that the air is being diffused inside the Naini lake, so that the aeration of the water happens. So, this is common. Similarly, if we go to swimming pool, so we will be finding that the swimming pool water is always aerated, and that may be aerated in the form of some fountain may be there any other place or nearby, and aeration is happening in different ways. And similarly, other places fountains are very common, and fountains are good method to aerate any water which contains some dissolved gases or otherwise. So, we will start with, so why we require aeration first thing, and where it is used. So, in the treatment plant, aeration is one of the first major process. So, it may be used individually also, and it may be there in the flow equalization basin also, if it is certainly part of inline flow equalization. So, this is there. Now, to remove aeration is used to remove dissolved gases. So, many type of gases like H2S, ammonia, chlorine, etcetera may be present in higher amount if suppose water is being taken from ground. So, and we have to use it further for drinking. Similarly, lot of wastewaters which are discharged from various industries, they may contain this high amount of dissolved gases. So, we want to remove these dissolved gases, we have to use aeration. So, lot of VOCs, volatile organic compounds, can be removed via using aeration. Similarly, some of the dissolved metals like iron, manganese, etc., can be removed using the aeration method. So, it is there already told it, this aeration unit may or may not be the part of the flow equalization basin itself. Aeration is also within the treatment plant. Aeration is very, it is a must for any aerobic biological treatment process. So, aeration is always done in ASP, activated sludge process, and some other processes as well. And aeration is done for not only for providing oxygen, because oxygen is essential for microorganisms to respirate, and during that process they use the various pollutants which are present in the water as nutrient, and you convert them into CO2 and H2O. And along with that, aeration is very necessary for mixing also. So, mixing helps in avoiding the settling of the various microorganisms which are commonly called as mixed liquor suspended solid in the case of activated sludge process. So, it avoids that mixing, it provides the mixing and avoids the settling of those microorganisms which are there. So, aeration is very essential, and it may take place at various places, and it may happen individually or along with the flow equalization basin. Now, there are many factors which affect the removal of compounds by aeration, and first and foremost are the physico-chemical properties of the compound or gases which are likely to be removed. So, these may be their hydrophobicity, the molecular size, surface area, etc. Similarly, temperature of the water and air, both are very important in aeration. We will understand these things in detail later on. Similarly, lot of process parameters which are there inside the which have to be designed properly in the aerator, like air to water ratio, what is the amount of air that we are using with respect to water. So, that becomes very important. Available area of mass transfer. So, this aspect we are going to study in detail, as well as the contact time, because it may require certain amount of contact time before actually the gases come out of the interface and go into the atmosphere. So, for this to happen, depending upon the amount of gases and compounds present in the water, it may require certain contact time, and that contact time is dependent upon whether the compound is hydrophobic, hydrophilic. So, all those aspects become very, very important in aeration. Now, what we will do is that we will start with some of the basics of the aeration before going further. And what are those basics? Now, if you remember that previously we had told that there is a certain solubility limit of any gas in water, and that gas, like for oxygen, it was in one of the questions, like the saturated oxygen concentration in the water is around 9.9 milligram per liter at 20 degree centigrade. So, this was stated in one of the lectures previously. Now, how do we know that okay, this is 9 milligram per liter at 20 degree centigrade? What will be the solubility limit at 40 degree centigrade or at 10 degree centigrade? And this is true for oxygen. What about CO2? Because CO2 is different gas as compared to O2. What about ammonia, nitrogen, helium, etc. So, for finding out what are the solubility limits, because these solubility limits are very important in designing the aeration unit, and we know the what is the saturation value. If there is high amount of gas is present in the water, so it can be removed only up to the saturation limit, it cannot go beyond. Similarly, if the gases are below the saturation value, they will always try to reach the saturation value. So, this saturation value is very important parameter, and it helps in the design of the equipments which are there in the aeration units. Now, going further, so one of the important laws or equations which are used for finding or calculating the solubility of gases is Henry's law. So, we use the Henry's law. All of us study these Henry's law, the basic definition in class 10th, 12th, etc. So, this is very well known. So, one of the basic forms of Henry's law is that the partial pressure of any gas in the vapor space above any liquid air interface is directly proportional to mole fraction of that gas in the liquid phase. So, suppose we have a beaker here and there is some water which is kept here. So, amount of any gas which actually be present in the vapor space, if it is suppose it is closed. So, amount of this partial pressure of gas will be proportional to the mole fraction of that compound in the liquid phase. So, this is called as Henry's law. Now, and the proportionality constant is called as the Henry's constant, which is given here. So, this is the basic definition, and now within that Pa is the partial pressure of any compound in the air, and the unit okay. So, this unit partial pressure may be in the atmosphere or any other pressure unit. Similarly, H is the Henry's constant which depends upon the temperature. So, for this particular equation which is given here, if we consider it 1. So, for this case its unit will be atmosphere. This is so because we have kept the partial pressure in atmosphere. So, whatever is the unit of partial pressure, that will be the unit of Henry's constant. Now, XA is the mole fraction of compound A in the water. So, this is there. Now, our aim from this equation is to find out the concentration. So, this is why we want that we know XA mole fraction. So, we have to convert the mole fraction into something like this, which is like concentration of A in water. So, concentration of A in water is basically what is this? This is solubility. So, this will give the value of solubility in the water. So, this is what we are going to find out, derive the equation, and this is very necessary for understanding many things. Now, by definition, if we go by definition, the mole fraction is defined like this: moles of compound A in the liquid solution divided by moles of compound A in the liquid solution plus moles of water in the liquid solution. So, what we are assuming that only A is dissolved in water, and that too pure water. So, we may proceed like this. So, in the second step, this now if we assume that moles of A in the liquid solution will always be very less, because it is only up to a certain limit and that limit is very less. So, it always is negligible as compared to the moles of water in the liquid solution itself. So, under that condition where we are assuming that moles of A in the liquid solution are much less as compared to moles of water in the liquid solution. So, in this case we can neglect the moles of compound A in the liquid solution, and the equation becomes like this. So, moles of compound A in the liquid solution divided by moles of water in the liquid solution. So, we can represent like this. Now, moles of compound A can further be represented as weight of compound A in gram divided by molecular weight of A. So, this is like molecular weight of A. Now, for moles of water, so what we are doing is that we are dividing this again weight by the molecular weight of water, and weight of water can be represented like density of water into volume of water. So, this is very easy to manipulate and we can easily do this. Now, once we do this, what we do is that we try to take out this molecular weight of the compound A divided by volume of water. So, this is our basic interest is there in this particular two things. So, we can manipulate little bit. So, this is the same equation is written, or what we can do is that for density we know it is around 1000 gram per this is 1000 kg per liter for water. So, we can take that idea. So, in 1 kg per liter. So, in place of 1 kg we are writing 1000 gram. So, this is 1000 gram per liter of the water, and 18 is the molecular weight of the water. So, that also we have kept here. Now, we can further manipulate this equation into such a manner that weight of compound A and volume of water, these are of our primary interest. So, we convert that into so this becomes Ca in gram per liter. So, this become, if we can write like this, so it will become weight of compound A divided by volume of water. So, this is there, and this is what is we are interested in more, and in addition there will be molecular weight of compound A. So, this is at the bottom, and similarly 18 will go up. So, 18 will be here and divided by 1000. So, these are additional terms which are there, and this actually is concentration of A in the water, and this is equal to 18 divided by 1000 into molecular weight of A. So, this is what is represented here, and now going further we can write the same equation, you can see here. So, this is the same written here, and so this way we can write X A as like this. Now, if X A is known, then what we can do is that we can use this X A in the equation which was written earlier, P A is equal to H A X A. Now, we can substitute this X A in this equation and then try to find out the concentration, because we want to write in terms of concentration. So, it becomes HACA into 18 divided by molecular weight of A into 1000. So, this will be there, and from that we take out the Ca. So, Ca in gram per liter will be equal to Pa into molecular weight into 1000 divided by the Henry's constant, sorry, this will be H, okay, and this will be 18. So, H with respect to A we can write like this also. So, this is in gram per liter, and in milligram per liter it will be 10 raised to 6 here. So, this way we can find out the concentration or solubility of any compound in water. So, this is the basic derivation or equation by which. So, for finding out this we require the Henry's constant. So, this is there. So, this also tells two things. The Ca is directly proportional to the partial pressure, okay, and also it is inversely proportional to Henry's constant. But this Henry's constant which is there, what is its unit, that is very important, because Henry's law or equation can be represented in different form. This is only one of the form, there are different forms, and in the literature or in the problems we will be finding that Henry's constant, the unit is always not atmosphere or any pressure unit, it may be entirely different units for H are represented. So, we are going to discuss that also. Now, going further, So, already told there are different types of Henry's equation possible. So, this is the one that we have discussed. So, in that case what we did is that Henry's constant was represented like kh, here it is represented by kh, we can write like h also. So, h or kh, here there is one thing more to remember, we have given some subscripts. So, and these subscripts are given because how the equation is used depending upon that subscript has been notified here. So, the first equation that we studied here, partial pressure of gas divided by mole fraction of that compound in the aqueous phase was there. So, this is there partial pressure of gas in the solution and x aqueous is the mole fraction of gas in the solution. So, if this form is there we write p x. So, this is p and this is x. So, that is why p x. For other cases this is like p c, then cp because and then cc. So, there are different notations, their units are different, remember their units are different and in the literature you will be finding all these forms. Okay. So, never get worried okay, that Henry's constant value has been given in different units, it is possible and we have different equations of same Henry's law which are represented in differently. Now, the second equation is that the Henry's constant is equal to the partial pressure of gas divided by the concentration of the compound in the aqueous phase. So, this is there. So, we can directly use to find out concentration, but this is the more common value. So, we use this. Similarly, the opposite also may be given. So, depending upon the unit what we should do is that we should try to see the unit which is given for Henry's constant, what is the dimensions which are given. So, generally it may be atmosphere only or any pressure unit. So, it is possible you can find that here atmosphere is there because mole will go off. So, mole it will be only written atmosphere for the Henry's constant, in this case this is there. Now, for the second equation it will be given like liter or meter cube anything into pressure unit divided by mole of gas. So, this is this is concentration mole per liter and partial pressure may be any pressure unit. Similarly, the opposite is possible and there is a dimensionless form also which is there. Now, going further there are the values of Henry's constant at for various gases in for the condition of water at 298 Kelvin is given here and the values are represented here and these have been compiled from this source. And now, all these values are for different gases like carbon dioxide, argon, oxygen, carbon monoxide, hydrogen, nitrogen, neon, helium etc. Now, these values are represented and these values are kept in this manner, the values are always increasing. Okay. So, this is one thing which is given here, the values are always increasing. Now, in the previous slide we had discussed that the C A is directly proportional or inversely proportional to H. So, that means if the partial pressure of gas is constant or otherwise we can put like this. So, we have a closed enclosure okay, and it is having certain what is there that water is suppose filled in this case and now gas is being pumped in. So, depending upon the vapor space which is there. So, if this vapor space is constant or the partial pressure of the gas is constant, then the solubility of gas will be always inversely proportional to the Henry's constant. Under same pressure partial pressure condition the solubility of CO2 will be highest, that means and solubility of helium will be lowest because it has higher value and since the C is inversely proportional. So, we will always the values are increasing in this manner, but the solubility will increase in this manner. So, that means, but this is only true for the condition where the partial pressure is constant, but partial pressure has lot of effect because in the natural environmental conditions the partial pressures are different Now, and we'll understand this by solving some problems. Going further, now there is always a variation of solubility of gases with temperature. So, the solubility of gases already we have learned in the temperature is one of the important parameters during physico-chemical characterization, and in physical characterization temperature is important because with increase in temperature the solubility of gases decreases, and solubility our interest is more in the oxygen. So, oxygen solubility also decreases. So, any thermal power plant etcetera, they cannot increase the temperature of the water beyond a certain value. So, that generally only 10 degree rise is permitted. So, this is there, and that is why the solubility of gases decreases with an increase in temperature. Now, if this is so, so certainly the Henry's constant will also vary with change in temperature, and that effect can be accounted for by finding out certain parameters. So, the change in Henry's constant with temperature can be computed using one type of equation. So, this type of equation is there, and where like here it is represented log 10 H is equal to minus of delta H divided by R T plus B, where R is the universal gas constant and its unit may be any other unit also, only one unit is given here, and delta H is the heat of absorption in kilocalorie per mole. It may be any other unit also, it is possible to change the unit or any other unit. Then T is the temperature in Kelvin, and B is a dimensionless empirical constant which can be used to find out the values of Henry's constant at other temperatures etcetera. Now, if we know the value of B and if we know the then we can find out the value of H at any other temperature, and if we can find out any other temperature we can understand that what is the solubility. So, this is very important thing, and this idea, not only this, the partial pressure is also very important. So, that is why in the if you go to purchase a canned cold drink, so any canned cold drink always contains CO2, and depending upon the pressure at which that can has been filled. So, what is the pressure of that can, whether it is 2 bar, 3 bar, 5 bar etcetera, depending upon that the amount of CO2 dissolved in that cold drink will be different, and if that is different the taste will be different, and also the cost will also be different. So, this is very important, and it depends upon H value, and once the solubility of CO2 is different, the pH condition may also change inside the cold drink. So, both temperature, partial pressure, they are very important factor in solubility of any gas inside the temperature. Today we will end this lecture, and we will continue with solving some of the problems in the next lecture, and then further continuing with other theories further with respect to how the oxygen transfer takes place inside any aeration unit, and what are the various resistances etcetera, and what are the factors along with the temperature that affect the oxygen transfer rate or the air transfer rate inside any aeration chamber or in bioreactors also, because most of the bioreactors also require oxygen, and there also there are a lot of resistance which are there. So, we can understand both aeration unit and biological reactors how the oxygen transfer takes place together. So, this way we are ending today's lecture and will continue on aeration topic. Thank you.